Okay, this is Cytogenetics Part 1 in 5 minutes. I'm going to go through this pretty quickly. First of all, classification of chromosomes. We have 3 different types. Metacentric is going to be where the centromere is in the middle of the chromosome. Submetacentric, it's going to be slightly skewed. There's going to be smaller arms and longer arms. And acrocentric, there will not be shorter arms. These are actually satellites over here. These are not actually chromosome arms. And there's only 5 chromosomes that are acrocentric: 13, 14, 15, 21, and 22. We'll revisit those. The P arm is the short arm in the metacentric and the submetacentric chromosomes, and the Q arm is the long arm. You can remember that by the Q arm. The Q has a long tail. Long arms, long tail with the Q. Now I want to talk about methods of chromosome analysis. Karyogram is basically just a figure. It's not an actual photograph like a karyotype is, but it does show you all the chromosomes in order and the bands where the genes are going to be, different loci here. How you name these chromosomes is in this section here. Basically, the chromosomes are divided up into different arms, like I discussed earlier, P and Q. Those arms are divided up into different regions, 1, 2, 1, 2, and those regions are divided up into different bands. And so you name it like this. XQ28 would mean chromosome X, arm Q, region 2, band 8. And we need to know how to do that. Continuing the methods of analysis, banding / karyotyping. This is an actual photograph done during metaphase. You can actually visualize the karyotype since the sister chromatids are going to be together. Then they're easy to visualize in metaphase because they're all lined up and they haven't separated yet. And you can actually see the banding pattern here. Fragile X syndrome you can visualize with this technique. You can actually see the fragile site on a mother carrier or on their progeny. Secondly, you have fluorescent in situ hybridization. You have fluorescent probes. You have to be in prophase or interphase to do this. And those will bind and complement to specific chromosomes. You'll be able to see the fluorescent visually, and you can visualize Robertsonian translocation and trisomy X like this. The last is comparative genomic hybridization. Basically, you can see a loss or gain of certain gene regions. It's the same theory as fluorescent in situ hybridization, except you have a metaphase sample from a patient or from normal. If more patient DNA hybridizes, then it's amplified. If more normal hybridizes, then it's reduced. And you can commonly visualize tumors like this. So continuing on, the cytogenic abnormalities. There's 5 of them that we're going to go through briefly. You have structural abnormalities like translocations. There's 2 different types of translocations. One is a reciprocal exchange. This reciprocal exchange means that it's reciprocal. There's 2 chromosomes that exchange the same amount of genetic information. There's the same number of chromosomes after it's done, but during anaphase and metaphase, this can cause problems. Whenever they split up, they do not line up properly. They form a quadrivalent. Alternate segregation, which is most common, produces balanced gametes, but adjacent 1 and adjacent 2 segregation does not. And so that's actually a problem. The second type of translocation is Robertsonian translocation. This is where satellite cells fall off of 2 of the acrocentric chromosomes. Acrocentric only can undergo Robertsonian translocation. This produces 1 less chromosome than what is normal. And remember, if you will, that fluorescent in situ hybridization, you can visualize Robertsonian translocation. So continuing, deletions, insertions, and duplications. Deletions go with insertions. If there's a part of a chromosome that's deleted, then it will be inserted somewhere else and vice versa. And if a part of the chromosome that's deleted is greater than 4 megabases, then it has a gross effect. Duplications are whenever there's expansion of a chromosome. It can be seen in a karyotype, and the carriers are going to be normal, but their offspring will be affected. Inversions can be pericentric or paracentric, and this is where you have a piece of a chromosome. There's 2 cuts to it, and it flips around and reattaches, except for backwards. And paracentric is not going to include the centromere. Pericentric will include the centromere. It can form these loops here. And if you have a null-centric, which means no centromere, or dicentric chromosomes, they will be non-viable. Rings can also occur. Ring is whenever you have a single chromosome that breaks and then reattaches to itself, it forms a ring. And then you have isochromes, where you have improperly divided chromosomes that actually the P and Q arms are divided instead of down the spindle. And then you get partial trisomy and partial monosomy. Thank you.